start now. We're going to look at two parallel current carrying wires and ask about the force. So that's putting two ideas together. A current carrying wire has a magnetic field, but a current carrying wire also feels a magnetic force when it's in a magnetic field. So what happens if we have two current carrying wires together? So let's start by asking, what does wire 1 do? So here's wire 1. Let's say that the current I1 flows up. Okay, it doesn't have to flow up, but we do have to pick a direction, so let's choose up. So wire 1 carries a current, so it makes a magnetic field. What's the direction of B1? Well, we know that magnetic field vectors around wires make big circles. So here's our wire, and it makes big circles around the wire. To get the orientation of those circles, you put your thumb with your current, and your hands show the orientation, your curled fingers. So over here on the right, the magnetic field will point down. On the bottom, it points to the left. The side, it points up. The top, it points to the right. So let's try and draw that in 3 dimensions. That's a little bit hard to do. Sometimes it's more useful to do a 2-dimensional picture. So there's our big circles. There's our 3D magnetic field. So the orientation comes up around this way. If we had a 2D picture, then this is our wire number 1 that has current 1. And right here at this spot, the magnetic field goes into the page. So our thumb goes up. What do our fingers do right there on top of that wire? They go into the page. This distance from here to here, we'll just call that our standard notation for a distance. So wire 1 makes a magnetic field B1 at the position of wire 2. So now what I'm going to do is draw wire 2 on top of this picture. So here's wire 2. So we see that wire 2 is sitting in a magnetic field created by wire 1. So wire 2 carries a current, and it's sitting in a magnetic field. How big is this magnetic field? Well, B1 is equal to mu naught times I1 divided by 2 pi times r. And the direction of this field is into page. So now wire 2 is a current carrying wire. It's in a magnetic field, so it's going to feel a magnetic force. Let's get a direction of current on here. Let's say that the current in wire 2 goes up. So there's our I2. So wire 2 feels a magnetic force due to B1. Okay, what is this force? So the force on wire 2, we'll call that force on 2. Let's get the direction first. So the current goes up, magnetic field is into the page. The direction of the force is to the left. So let's draw that in. F on 2. So F on 2 is equal to I2 times L crossed with B made by wire 1. I'm trying to be really careful with notation here. Getting the direction with our right-hand rule, so I'll just put RHR here. So that force is I2 times L times B1. I could say to the left, but I want to stay a bit general. You know, what if I rotated my wires or something? I'm going to say towards wire 1. Because no matter which way I rotated it, that force would point towards wire 1. So now let's fill in what I know for B1. So I2 times L times mu naught I1 over 2 pi r. There's our magnetic force, and it points towards wire 1. Okay, so we've got that done, but you might be asking, well, what about wire 1? Okay, let's do this again. So what is the force on wire 1? And let's do this guy just a little bit faster. Okay, we'll just do the same idea again, but we won't take quite so long about it. So the force on wire 1. So we have wire 2 right here. It has a current that goes up, I2. That current makes a magnetic field that makes big circles. So our thumb goes with the magnetic field. Our thumb goes with the current. And what are our fingers doing right here where I1 is sitting? They're coming out of the page. So there's our magnetic field due to wire 2, B2. Wire 1 sits in that magnetic field and has a current that points up. There's I1. What's the direction of the force on this current carrying wire? Current is up, magnetic field is out of the page, so our force is to the right. So there's the force on 1. See that it's towards wire 2. Okay, that's the same thing we did in the previous steps. We just didn't write down nearly as much stuff and we went through it a bit faster. So B2 is equal to mu naught times I2 over 2 times pi times r. Our force on 1 is I1L cross B2. So then that force is I1LB2 towards 2. So then we can say that that's I1 times L times mu naught times I2 over 2 pi r. Okay, let's have a look at this for a second. This force, the force on 1, has the same magnitude as the force on 2. Does that make sense? I would have to say, yeah, that makes a lot of sense. These two forces are equal and opposite. So if 1 has a force on 2, then 2 has an equal and opposite force on 1. That's Newton's third law. So it's good to see that Newton's third law is still good. So that's worthy of putting a little note in here. So F on 2 equals minus F on 1, and we'll put in brackets Newton's third law. So that makes sense as a result. Then last, we'll just put in a general observation. In general, the force between two current-carrying wires, I'm just going to call that FB, is equal to mu naught times I1 times I2 over 2 times pi times r. The direction of the forces are attractive if the two wires carry current in the same direction. And we didn't go through this process. This might be a good exercise for you to try at home. But it would be repulsive if the currents were in opposite directions. Okay, so there's our talk about force on current carrying wires. What we'll do next is a couple of examples.